While the texture or relative proportions of sand, silt, and clay is an important inherent property of soil that is not readily changed, soil structure, or how particles are grouped together into aggregates by chemical, physical, and biological processes, is an important aspect of soil function and overall soil health that can be modified by management. Pore space in the soil is created both within and between aggregates, and it leads to the retention and exchange of air and water in the soil. Aggregate stability refers to the ability of soil aggregates to resist disruption when outside forces that are usually associated with water are applied. Water-stable aggregates resist disruption from rainfall at the surface and water movement through the soil. The breakdown of aggregates, when struck by raindrops or irrigation waters, or under conditions of high soil sodium, releases individual soil particles that can then clog soil pores and seal the soil surface. Soils with higher content of organic matter tend to have greater aggregate stability than the same soils with lower organic matter. Thus, additions of organic inputs to the soil in the form of compost or from cover crops increase aggregate stability. Soil microbial communities decomposing these inputs create breakdown products that glue together soil particles and grow fungal mycelia that help hold together aggregates. Paying attention to the structure or the stability of aggregates in farm fields is an important diagnostic indicator of overall soil health. Aggregates provide a visual indicator that farmers and land managers should be familiar with and keep track of. Aggregate stability is sometimes measured using detailed protocols and laboratory instruments that subject aggregates to mechanical dunkings or controlled wettings to measure the degree to which aggregates fall apart, disintegrate, and fall through a sieve screen. From this, the weight of the aggregates that survive this process is compared to the original weight to determine the proportion of stable aggregates. With increased attention to the importance of soil health and what management practices can help achieve these goals, more user-friendly techniques are evolving to readily assess soil aggregate stability even in the field. One such method, shown here, is part of various soil health assessment toolkits. A soil aggregate is put onto a pre-mounted screen and submerged for 5 minutes in water. The extent of aggregate breakdown is then scored during that time, and then after 5 gentle dunkings by hand. This simple, quick assessment technique can provide estimates of aggregate stability that can then be compared over time. A second technique makes use of the mobile phone app Slakes, S-L-A-K-E-S, and involves dropping a soil aggregate in a plate of water. The phone camera calculates a starting aggregate circumference and then compares that with the final circumference after 10 minutes. Aggregates that readily dissolve during the 10 minutes have low stability, whereas those that resist dissolving have higher stability. The Slakes app has been evaluated in a major project by the Soil Health Institute that showed promise of this technique as a quick and easy method for gauging aggregate stability. Despite the importance of soil aggregation in agricultural productivity, identifying management practices to improve and regenerate soil aggregate stability has been underappreciated in many California cotton production systems. A unique 2-decade-long study that included 12 years of cotton cropping in 5 Points, California, found that aggregate stability, measured by wet sieving and the Slake's mobile phone app, were more than double in fields that were managed with cover crops and no tillage than fields with neither of these soil health practices. Aggregate stability in the cover crop and no-till managed system on the left is now dramatically different from the conventional tillage without cover crop system on the right. Increased soil aggregation was correlated with increased soil water infiltration. Shown here is the time that it takes for 1, 2, 3, and 4 inches of water to infiltrate into the soil. Water infiltrates into the no-tillage cover crop soil far faster than into the standard tillage with no cover crop system. Broader implications of these findings may help farmers to better manage the water cycle in their cotton fields, as seen by work in Tennessee, showing cover crops and no tillage improve soil function, cotton yields, and soil water content, 28.6% with cover crops and 36.4% with no tillage. In 5 Points, we also found significant increases in soil water content in winter cover crop fields relative to clean cultivated soils. The cover crops were terminated in March of each year, then mowed, and the residues were converted to soil surface mulches that contributed to reducing soil evaporation, compaction, and sealing. In California's Central Valley, severe water shortages, large weather variability, and extreme weather events threaten agricultural production. Recent projections of UC Davis researchers, however, show potential to reduce groundwater overdraft by capturing water from what are called high-magnitude stream flows or flood flows. Increasing soil aggregate stability and rates of water infiltration may also help immensely in achieving this goal. Most of the cotton produced in California, however, is grown in regions that get relatively little winter rainfall. Nonetheless, creating good soil aggregates by practices such as reduced disturbance tillage, compost application, and winter cover crops is important in extremes of both too little water and too much water. Good aggregation helps not only in drought, but also in permitting as much water to enter the soil as possible if rainfall patterns shift toward more intense rain events. This increased infiltration also leaches salt out of the soil. None of this, though, is new. The Soil Conservation Service in California, back in 1938, recognized the importance of capturing or keeping the raindrop where it falls by the use of good soil management practices such as cover cropping and no tillage. It is exciting to see that recent research demonstrates the potential of using these practices in current agricultural production systems, and that can achieve economic yields comparable to those of standard tillage systems, while simultaneously improving soil health. We hope that the information and soil health management options presented in this video for improving soil aggregate stability will result in greater appreciation of the importance of preserving soil structure in California cotton systems.